Hi, and welcome to this edition of the Battery Management Systems Seminar. My name is Jeff Phelan. I'm an applications engineer in TI's Battery Charger Group. This presentation is about resolving battery charging common application issues. Quick agenda, we're going to review the lithium-ion battery charging profile and charger topologies, and then we'll jump right into the most common issues that people trying to develop battery charge applications come into. Essentially, I've grouped them into battery not charging, having too long of a charge time, or some sort of thermal issue because of the really high charge currents that you want so that the battery charges as fast as possible. So here is a summary slide showing a complete lithium-ion battery charging profile. It's recommended to have a trickle charge portion when the battery voltage is very low, typically below around 2 volts or so. Then you can jump into pre-charge, which is a slightly higher charge current when the battery gets a little bit higher, say somewhere around 2.8 volts. Then you will hit the constant, the fast charge or constant current phase of the charge cycle, where you charge at the fastest charge current that the battery can handle, which is usually around the 1C rate. And then eventually you will hit the maximum battery charge voltage or battery regulation voltage, and that's the constant voltage or voltage regulation portion of the profile. And at that point, the charge current naturally tapers down due to the undesired resistance between the charger's bat pin or the remote sense pin and the actual cells that are in the battery pack. And then if for some reason the battery's damaged, all the chargers do have a safety timer to stop charge if they don't eventually terminate. The simplest type of charger is a linear regulator-based charger, and one that is also uses external resistors to set things like the charge current. We call those at TI a standalone charger, and you can see on the right-hand side, the simplest one I chose was the BQ24040, and it has resistors to set the charge current, but also the pre-charge current and the termination current with 2 different resistors. You can also set the input current as well with this particular charger. But inside the charger, there are 2 feedback loops, one to monitor current and one to monitor voltage. I've got those highlighted in blue and green. And then the chargers also have comparators for some sort of input protection, such as under voltage if the battery voltage is the input voltage is too high, over voltage if the input voltage is too low. And then we also go into a different state called sleep if the input voltage isn't high enough to charge the battery. So in a buck configured, which all linear regulators are buck-based, you would have to have the input voltage higher than the battery voltage in order for the charger to charge. Standalone chargers also do have status pins, typically at least a charge pin that will indicate that the battery is charging, but they also may have a PG pin to indicate that the input power is good. The benefits of the standalone charger are they're simple and there's no software required, and you can use external resistors and typically swap them out potentially if you want to change either the input current or the charge current at some point. And then some of the chargers actually, like this one, the 25616, has a pin where you can change the regulation voltage from like 4.2, which is the typical, to 4.35, to a lower voltage of 4.1, depending on where that particular pin is set. If you do use the external resistors in the data sheet, you'll see that we specify a K value, which is the proportion of the input current relative to the resistance that you set. The limitations of a standalone charger are the pre-charge and term currents are typically a fixed value, so they're it could be some 10%, like typically a 10% of fast charge. If they don't have a pin like that 24040 did to actually let you set those independently. The resistor tolerance affects regulation accuracy, so you want to make sure these resistors that you pick are at least 1% accurate resistors. As I mentioned, you can dynamically change the charge current, for example, but you would need an additional resistor and maybe a FET that you would turn on and off to put another resistor in parallel with the primary resistor to change the charge current. And you do have limited status reporting. If you've only got one stat pin, it's either low or high or potentially blinking to let you know that there's a fault, but a blinking would indicate numerous different faults, so it might be a little bit more difficult to debug. Here is a block diagram of a host-controlled switching charger. So this is a buck-based switching charger, and as you can see, it's also what we call an NV or narrow voltage DC power path charger. So you can see the input to the buck converter is actually this P-mid pin, and the high side FET Q2, low side FET Q3, and then we have a BAT FET. So the output of the buck converter goes to the sys pin, and so that's where you would attach a system load, and then the battery actually attaches at the BAT pin. So the BAT FET actually can more accurately measure the termination current, and it allows us to have, since the battery is separated from the system output, the converter can actually provide a minimum system voltage at sys, so that, or in the event that the battery is so discharged that it can't power up the system, the converter itself will do that. Just like the standalone, we do have comparators for the state machine to determine which phase of charging, or if you're in some sort of fault state, and also monitoring UVLO overvoltage. We monitor BAT overvoltage, and then similar to what we saw on the standalone, we do have feedback amplifiers that in this particular case, instead of modulating the gate of a pass element like we did on the linear charger, we actually modulate the duty cycle of the PWM modulator to regulate either the system min voltage or if the battery is too low, or the battery voltage once we get to constant voltage regulation, or charge current. But we can also monitor and regulate input current to make sure that we don't overtax the power source, and as a last resort, the input voltage, if in the event that we do for some reason pull too much current out of your power source and we don't want to collapse that power source completely. And we're going to jump into a little bit more detail about how these other loops work later on in the presentation. The main benefits of this, what we call a host-controlled charger, in other words, one that either has I2C or SM bus to allow a host to communicate with it, is those the registers that are you can write to with I2C or SM bus are used by the state machine or the internal loops to determine where to make decisions, right? Like at what set point is our input OVP, or where is our battery regulation voltage? What is our charge current? And because we do have quite a number of steps, like this particular device, the 2579X family, we can go constant voltage charging from 3 volts all the way up to 18.8 volts in 10 millivolt steps. We have I pre-charge and I term all the way down to 40 milliamps and up to 2 amps in 40 millivolt steps. Constant current charging, we can set from 10 milliamps all the way up to 5 amps in 10 milliamps steps. And then we have status and fault registers that will tell you exactly what state that the charger is in. If you're in constant current, constant voltage, if you're in input current limit, if you're in input voltage limit, if the chip has gotten too hot and you're in thermal regulation. There are also status and fault bits that will report if you have some sort of OVP. And then this particular device also has an integrated ADC where you can get the instantaneous measurement of VBus, VBAT, IBus, IBAT, or the die temp. The key limitation of the host controlled is host software is required. But just note that the precision that you can get with a host controlled is typically higher than what you can get with the standalone, simply because you don't have the variation of the external resistors, unless of course you buy a really, really expensive, high tolerant resistor. But using the host controlled gives you more precise values. So the most common issue that we have, or most common complaint that we get, especially on the EDE forum, is that my battery isn't charging. So I'm just going to flip through some of the more common problems that we've seen. As I mentioned previously, we do have these comparators that monitor the input voltage to make sure it's either high enough or not too high to charge. You know, all of our parts have an absolute maximum voltage, and then we always make sure that we keep the input voltage lower than that absolute maximum to make sure the IC isn't damaged. But we do still have to have enough voltage to make sure that the charger can turn on and that it's linear regulating LDO, which provides the power rail to all the internal circuits, has enough power so all the internal circuits can turn on. We also look at the input to make sure that even though you might have enough voltage, you got to have enough current. So we have a little power source circuit where we pull current and make sure that that input voltage bus doesn't collapse. And as I mentioned previously, we do have the OVP circuit to make sure that the voltage isn't too high, either that we get too close to apps max, or we may be too high, especially in the case of a linear regulating charger. It'll be impractical for the linear regulator because it will get too hot because it's if the drop across the pass FET is too large. Another case that we've had is all of our chargers have a charge enable pin and a charge enable bit, and both of those have to indicate charge. If either one of them says you can't charge, then charging stops. So both of those have to be configured, one with hardware and one with software if it is a host controlled part. And then the Regan or LDO output pin can have a minimum amount of current on it. It can be used for other things, and we always spec in the test conditions how much loading that you can have before you fall out of regulation. So you want to make sure that you don't put a large resistive load that will cause the part to go out of regulation. Another issue that we've seen with the battery not charging, especially if you're testing on a test bench, is all of our chargers have a TS pin, and that's short for temperature sensing, and it's intended to connect to a thermistor. Now we do have two different types. I'm only showing the voltage regulating type of TS pin. We do have a current type where the only thing you connect is the thermistor. The voltage regulating type allows you to use a resistor of different sizes. The current type requires you to use, for example, a 10 k ohm thermistor or a 100 k ohm thermistor. But if you don't have a voltage that is roughly 50% of the reg-in voltage at the TS pin, then the charger thinks that there is a fault, a temperature fault. In other words, the battery is either too hot or too cold. And all of our parts have, at a minimum, in as shown, and the right-hand side is have JEDA temperature charging, which means that we can charge the battery between 0 and 60 degrees, but between 0 and 10 degrees, we have to lower the charge current from the maximum. And then from 45 degrees C up to 60 degrees C, we don't want to charge to the full voltage, so we lower the battery regulation voltage. So when testing, especially on the bench with a simulated battery, for example, you want to make sure that you do something with that TS pin, or you will end up with a fault and the charger will stop charging. If you do have an NVDC charger with a separate sys pin, the converter will still function, so you're still get a sys voltage, but you'll just stop with the charge current. Another instance where you're not charging is it could be timer related. So some of our chargers have a pre-charge timer, and for the standalone parts, that's typically a fixed value. And then some of the host-controlled chargers, it is adjustable. And then all of the chargers do have a fast charge timer or safety timer. With the standalone parts, it could be a fixed value, or it could be set by a capacitor. But regardless, you want to make sure that you set the charge current high enough to get the voltage above whatever threshold is needed to make sure that the safety timer or the pre-charge timer doesn't expire. And as you can see, some of our host control parts allow you to set different fast charger times from 5 hours all the way to 20 hours on this particular device. And then, although not recommended, we do allow on some of the devices to disable the safety timer. And then, of course, if there is a safety timer fault, we definitely want you to investigate and figure out why you're having that long charge time instead of just trying to disable the fault. And then most of the chargers, if you do have a safety timer fault, you can just toggle the CE pin or CE bit to restart charge or change the timer I2C register. And then for the pre-charge timer, if there is a problem that the battery hasn't charged above the VBAT UVLO threshold, then you need to probably increase your pre-charge current setting if possible. The next most common issue is long charge time. So all of our I2C chargers have a watchdog timer, and the watchdog timer is intended to connect with a host, and the host sends a periodic ping to a register, and that tells the charger that it is that the host is still available. And then you can see in the bottom left that we do offer different watchdog timer settings, and we also offer the option of disabling the watchdog timer. The issue with the watchdog on these parts is if the watchdog expires for some reason, then several of the registers can be reset. So your input current limit could be reset to a lower voltage. Your charge current could go back to a default, which could potentially be a lower voltage. The safety timer could reset. Your battery regulation voltage could change back to the default voltage. Your JEDA settings could reset. And in a few cases, we actually have some where the default for the charge enable bit is actually disabled, not enabled. So definitely monitor and make sure that the watchdog timer is doing what you want. In general, we don't recommend that you disable a watchdog because it is considered a safety feature. But hopefully you can modify your software to maybe ping more frequently. But if there is a case where you're going to be running standalone without a host, then you kind of have no choice but to disable the watchdog. You just have to make sure that the default settings are enough, are high enough, like the charge current, for example, to get you your battery charged before the safety timer expires. Another problem resulting in long charge time is if the input current limit loop engages. So over on the right-hand side, you can see the a simplified block diagram, and the bottom two amplifiers are our what we talked about, the constant voltage and or constant current loops that tell the PWM for this buck-based charger to turn on and make sure we're providing enough output power to get the output charged. Well, the input current limit, or INDPM loop, actually monitors the input current from your input power source, whether that be a USB port, a wall adapter, or whatever. And we want to monitor it and compare it against a predetermined or a preset value to make sure that we aren't pulling too much out of that input source. So basically, we know how much current that input source is supposed to have, and we want to make sure that we don't pull more than that out of it. If you do end up pulling too much out of it, then this loop is going to kick in, and it's going to clamp the PWM signal, which means that our output power is clamped, and that will end up reducing your charge current in the event that your system current is still pulling current. So as you can see with the graph at the bottom, the system current is at a certain, consistently going up, and that's no problem because our input current is high enough to handle it, so we get the charge current we want. And then, but then at some point we hit this maximum input current and we stop. And so that means that the system current now has to drop. The system current still takes priority, so we still are providing power to the system. We don't want the system to collapse, but that means that the charge current has to go down. So the charge current now gets reduced because you're being input power limited. And then eventually the system current drops and we return to that amount of charge current that we want. So the solution for something like this is, well, first try to reduce the load on system. If you can't do that, then you want to increase your power source and or potentially your input current limit pin or input current limit register setting. The parts that we have that do have an ILM pin, the I2C based or host controlled parts that we have that have the INDPM register and also an ILM pin, that the ILM pin is actually a clamp. So the charger actually takes the lower value of the charge current or the input current set by the ILM resistor versus the input current limit register. So you want to make sure that the ILM resistor is high enough and or your input current limit register. Now some of our parts have D plus D minus pins that will automatically try to set the input current limit or INDPM register at power up, and that may result in too low of a setting, for example, so you might want to change that if after the USB enumeration happens and you've determined that the D plus D minus either was incorrect or you're able to now get more power out of your USB source. Another reason for long charge time is the input side impedance. So none of our setups or applications are ideal, and we always have parasitic what I'm calling parasitic resistance, and I've indicated it here, which is a single resistor, but that resistor is going to be the resistance of the adapter USB port connector plus the cable, and plus the resistance on the PCB itself. So that means any voltage going across that resistor results in a voltage drop seen at the charger itself. So let's say you had a 5 volts USB port, and you but the input current across that resistor reduces that voltage seen by the charger at its input pin, the V-bus pin, for example, down to like 4.8 or something. So that can cause some issues for the charger. The solution would be to obviously use a higher quality cable or connector and make sure that your PCB has really, really good, thick copper layout. But we also have another loop where we monitor that input voltage, because we don't want to crash, especially like a USB port, we don't want to crash that voltage by pulling too much current. So similar to the input current limit that we looked at previously, the VNDPM loop monitors the input voltage against a preset value, and if the input voltage dips, then like we saw before, as the system comes up and the input voltage droops because we're pulling more input power, then all of a sudden we have to start reducing the charge current to make sure the system keeps its power and doesn't collapse. Now, when setting that VNDPM threshold, you want to make sure that you don't set it too low so that the charger ends up in like 100% duty cycle. Most of our chargers can't actually do 100% duty cycle. They still have to have just a little bit of headroom. And but at the same time, you want to make sure that you don't set it too high and therefore not get enough power, and therefore reduce your charge current to the point where you don't charge and let the safety timer expire, for example. But the goal of VNDPM is to make sure that you don't overstress or collapse the input voltage because of some unknown issue, or for example, a really poor quality, cheap cable that has high resistance connecting the power source to the charger. And sort of along those same lines, you can sort of think about it this way. So you need to make sure that you have enough input power to provide both your system and your charge current. And you can see the legacy USB battery charging 1.2 spec or limit. You can see here that you are somewhat limited, and if you wanted to charge it, for example, 3 amps, you would need 15 watt input to get all the way to 4.2. So the legacy USB adapters could provide maybe 5 watts and in some cases 10 watts. But by the time you have your connector current limit, some of the connectors are rated for like 1.8 only. And then if you have a cable I times R drop, let's say, for example, 300 milliohm resistance for a cable times 1.8 amps, then you're going to have not as much voltage seen by the charger. So the only solution to that would be to try to get a higher efficiency charger to make up for the fact that it has a lower input power, so that we're getting the maximum power. So this graph on the left actually assumes that we only have a 90% efficient charger, which nowadays would be considered not a good charger. But the next option would be to change to a high voltage adapter, and what we call a high voltage DCP, where DCP is a USB term, dedicated charging port. So these adjustable high voltage adapters, essentially what they do is they negotiate with the input adapter through some sort of handshake, and then change their output from the USB 5 volts to potentially 7, 9, or 12. and they do that based on D plus D minus signaling. And you can see the figure over on the right that how the D plus D minus lines change to certain levels, and then the bus is jumping from 5 volts to 9 volts. And then now that we have USB Type-C with power delivery, you have the option of doing something similar, but with slightly more complicated communication. So you can go from 5 volt 2 amp to like 20 volt 5 amp, for example. Those particular USB Type-C ports with power delivery do require communications across the USB-CC 1 and 2 lines. Currently, TI doesn't have any chargers that do that because that type of communication is very complex and basically requires a little processor. And all of our chargers right now are based solely on an asynchronous state machine. So you might need, as shown at the bottom right, a USB port controller like the TPS 25750 in order to do the negotiation to get the higher voltage from the USB Type-C port, and therefore the higher power that you can then send to the charger, which is the BQ25792. And this is actually a reference design that you can find and order a board for in the BQ25792 product folder. Another instance of long charge time could be due to output side impedance. So just like we had a problem on the input side, you can have what I'll call parasitic resistances, like the PCB itself, and then the connector, and then inside the battery pack protector, you have the resistance of the protector FETs, and then of course the impedance of the battery, which, you know, as batteries age, they get slightly more resistive. So there's not much you can do about the protector FETs or the impedance of the battery, but so if you to reduce the charge time, of course, with any charger, you can increase the termination current. That just means that you won't fully charge the battery cells. We do have some devices that have what we call our IR comp. It's just a simple algorithm which artificially increases the bat reg. So let's say that your battery should only be charged to 4.2 volts. Well, we have a little routine where you set the amount by which you want to raise that battery regulation voltage, and to offset for this known drop of resistance, and then that allows the charge current to increase. So you can see the green charge current, once we've hit the a certain value, we actually increase the battery regulation voltage so that the voltage sensed at the bat pin by the charger hasn't met the CV level yet, so hasn't met the battery regulation voltage yet. So therefore we can increase the charge current, and then you can see that the charger at least thinks that the battery's at a higher voltage with the curve at the top, and then the current itself continues longer at the fast charge pace and then starts tapering later, and then we charge later. Now this concept, you don't necessarily have to have a charger that has the IR comp. You could do the same thing with host software, but our device actually does have a sort of an extra register to make sure that you have an extra protection and that you don't end up overcharging your battery. So if you do that, just make sure you understand and have a way to protect against overcharging the battery. And then the last solution would be to pick a charger that has a remote sense. Now the remote sense is probably only going to help you accommodate the PCB parasitic resistance, potentially a connector resistance as well, but it can't help with the protector FETs or with the changing impedance of the battery. And as I mentioned earlier, all of our chargers have another loop, which is the thermal regulation loop. So we always monitor the die temp of the charger to make sure that the die hasn't exceeded a certain value and could therefore damage the IC. Usually it's somewhere around 125 C, but we do monitor that, and then if we if the die temp hits that level, we again clamp the PWM duty cycle, and that would cause the charge current to reduce. So the solution to that would be to improve your PCB layout and heat sinking for the charger. So that sort of gets into board layout and heat sinking. So a lot of our chargers are in QFN packages with power pads on the bottom, and the goal of that is to allow for better heat sinking by connecting that power pad, which is also tied to ground, with vias to large ground planes. And you can see that in the diagram at the bottom right, where the sort of yellow-orangish with the darker orange circles are the vias, and then the orange itself is the ground. And then that is being down to the pink, which is the internal or second layer, which is all ground. So that allows us to distribute that heat and hopefully not have the device enter thermal regulation and therefore reduce your output current. Now, I did want to kind of throw in a little talk about lower EMI. So all switching chargers have the potential to emit noise up into some higher frequency ranges, and so the diagram at the lower left shows us the problem current flowing loop that we have. So in a buck converter, you go from the input cap through Q1. So Q1 is actually, in this particular instance, this is our reverse blocking and input current sensing FET. So Q2 is the high side buck FET, and then Q3 is the low side buck FET. So we would turn on Q1, Q2, current goes through L1 to sys, and then makes a loop that way. And then when Q2 is turned off, then we turn on Q3, and we have current that flows from ground through L1 to the output at VSys and the cap. So the problem comes in and when those Q2 and Q3 are switching on and off, and any parasitic resistance and then the parasitic capacitance that is so the parasitic resistance that's in series with those FETs, and then the parasitic capacitance that's across those FETs, and then any kind of ground return that's really long and doesn't go back close to the ground pin, that results in this high frequency loop when those FETs are turning on and off, and you end up with ringing because you have little LC tank circuits. So with a buck converter, the goal would be to minimize this high frequency loop return, especially the ground return, and that means that this input cap, this CP mid cap, is the most critical. So you want to make sure that that CP mid cap is as close as possible and has a really good connection to the ground of the ground pin of the IC. And as you can see on the diagram, we have a lot of vias that take us back, and then the two pins over on the right-hand side that connect directly to the ground of the sys caps, those are the ground pins of the IC. So the priority for any kind of buck converter, and then also if, for example, that this is running in reverse as a boost converter, that PMID cap is critical to make sure that you have the lowest EMI possible. Most people try to put the inductor as close as possible to the IC, and actually that's probably your lowest priority. The goal is the CP mid cap, and then the reg in cap, then sys and bat cap, and then the inductor. Because if the inductor is pushed further away, you're really adding resistance and inductance to an inductor. So you're not really changing that performance that much. The only caveat to that is the bigger that trace or plane or whatever it is that you connect from this charger's switch pin to the inductor, that you want that to be kind of narrow and probably not have ground under it. So this probably should have not shown the pink second layer as being cut out, because that will just sit there and move up and down and look like a capacitor and spew stuff, bad noise that we don't want. In the event that you do have the board or case temp exceeds your thermal budget, then you do have to do a lower charge current in order to make sure you don't exceed your thermal budget. Really, the only way to do that is you probably would have to relay out your board and increase the number of board layers to allow more additional heat sinking or add airflow, and then to make sure that the ground, especially if you have a ground ped, that it's tied to as much copper as possible, and then also any of the power pins, so VBus, PMID, sys switch, and also be connected to as big of planes as you possibly can. If you can, especially for the integrated FET chargers, you want to make sure that you don't put other high power consuming ICs close to that, or use ground for them, heat sink them close to the charger to make sure you don't saturate your big ground heat sink that you're using. And then you can obviously change to a more efficient charger if you have to. So over on the left, you can see this is our BQ25890. It's in a 4x4 QFN with vias to the internal and bottom ground layers. And with VBus of 9 volts, a battery at 3.8 volts and a 3 amp charge current, we were still seeing an IC top side of 41 degrees C, which is reasonable. The 890 is several years old, so we have so much higher efficient chargers now. But this gives you the general idea of how hot that you can end up when you're trying to charge at 3 amps and above. So that leads us right into, if you have very high charge current, so something that's like 3 amps and above, then it does become challenging sometimes to make sure that you can meet your board thermal budget. So as I mentioned, we do have higher efficiency chargers. So the and also we have chargers of a slightly different topology. So the first two in the table are just standard single cell chargers, standard 2-level buck, and comparing them, you can see that, for example, the 2561X has a high side RDS on of 62 ohms and a low side of 71 milliohms. Excuse me, that slide needs to say milliohms. And you can see the efficiency. So that's actually at 89% efficiency for a 9-volt 3.8 and 3 amp charge. And at 5 volt, we get a slightly higher efficiency, which we should, right? Because the bus voltage is closer to the battery or the output voltage. And then we have the 898, which has lower RDS on FETs and therefore slightly higher efficiency. Because our losses are a function of the DC losses, which would be the RDS on drops, the voltage drop across the resistances of the FETs, as well as in the inductor. But then we also have switching losses too. So now the 25910 is actually a slightly different topology. It's a 3-level buck. And even though it actually has slightly higher RDS on because of its topology, it actually has much higher efficiency. So sometimes you do have to look and make sure that you don't have that you have the correct topology for your application, or you might have to lower your RDS on. Lower your DCR of your inductor, for example. And just to sort of highlight that point, small efficiency increases can give you a much higher charge current. So comparing from that table before, let's say we had a 1.5 watt loss budget, the 25898 can give you a charge current of 3.2 amps before it will hit that because of its efficiency. But because the 25910 is more efficient, we can actually get all the way up to almost 4.3, 4.2 amps. And then as highlighted in the curve on the left. And you can see the thermal performance of the two on the right. So the 910, because it's more efficient, the IC gets to 44C, but the 898 gets to 52C. The 910 in its three-level topology, it ends up being a 36% smaller solution size and a smaller inductor, and is able to provide more charge current. The next level that you would start considering is if you don't want, is between an integrated FET charger versus a charger with external FETs, or what we call a charge controller. So the benefits of a charge controller are that you can place your power FETs around the board and therefore distribute their losses across the board. And as you can see, the one I've referenced here is the BQ25713. The IC itself is 4x4, so and so it will have a area of 16 millimeters squared. It's not going to really dissipate a whole lot of heat, but by the time you add in all these FETs that you need externally, their power dissipation will be distributed, and then we do have external sense resistors for our controllers. So your area, PCB area that you need for this particular charger is going to be bigger, but you can, distribute that heat around, as opposed to on the right-hand side, a charger like the 25790 with integrated FETs, and depending on which package you choose, you can have a significantly less area, but all the power dissipation is going to be in one spot. So you have to make sure that you do have a way to heat sink these chargers, the integrated FET chargers, significantly, or they will get too hot and then run in thermal limit. Another option, if you did want to use integrated FET chargers, for example, and not go to a controller with external FETs, is to use two FETs in parallel. So we typically would have one, what we call a primary charger, that provides trickle charge and pre-charge, like the 25620. And then we might connect a secondary high efficiency 3-level buck charger like the 25910 that we talked about. And we connect them both to the same input, and we tie the bat pins together. Now the 25910 is not an NVDC charger, so that would mean that it doesn't have a sys pin, and all of the system load will still come out of the 25610. But that allows you to at least somewhat distribute the power, because the 25620 can still provide charge current as well as the 25910. The only caveat to this is you do want to make sure that you stop probably the 25910, and so you set its either termination current higher or its battery regulation voltage lower, because you don't want to have both of them trying to terminate at roughly the same battery voltage, or you will end up oscillating because you're essentially tying two voltage sources together at the same point. And then another option, if you have a very specialized adapter that has a processor in it, you can use a switch cap charger that is able to communicate with a smart adapter, or maybe a USB-C PD, to provide only the minimum headroom needed to charge the battery across essentially a linear pass FET. Now, these particular switch cap chargers are only designed to do the constant current. They typically don't do the termination, so you would still need a device like the 25620 to do the trickle, pre-charge, and termination. So in a sense, you are still putting two in parallel, but these particular chargers, because they're just linear charger across a pass FET and you're modulating the input voltage, you can end up with 97 or higher efficient power stage and get 8 amps of fast charge current. So in summary, all issues are solvable. If your battery isn't charging, then you just want to make sure that you understand that you're getting enough power, that everything's turned on, that your safety timer hasn't expired. If you have too long of a charge or extended taper time, then you want to optimize your INDPM or VNDPM settings, maybe switch to a high voltage DCP adapter to reduce the drop across the resistance, the input resistance. And in the event that you're hitting thermal regulation, you want to improve your heat sinking with good PCB layout. And then if you have very high charge current, or you want to have a very fast charge time, or you have a very large battery, then you want to use the highest efficiency charger available, potentially move to a charge controller or maybe parallel chargers. And I guess next we'll go to, if we have any questions, you can try to scan this and provide feedback on this presentation. And that's it. Thanks for attending my presentation.